Hey, Kevin, how's it going?
Great.
Good, good. So I'm going to be here today, but don't call on me because I'm going to be working on my other computer. But I am here. If you kind of wave, you should catch my eye. Okay.
Okay. Yeah.
Right. I'm going to mute myself so you don't hear me talking to myself. Okay. Hey, good luck. Do you need anything from me?
No. I guess just wait for them.
Okay. Sounds good.
Hi, Kara. Hi, Kara. Welcome.
Hello.
Okay. Since you've come, I'll just begin the meeting.
Okay.
Yeah. So today we are gonna introduce two things. Oh, okay. The first one is recursion. Yeah, we're just gonna talk about recursion. So to get a definition of recursion, so if we Google recursion, right, we'll see some results. Also, it asks us, did you mean recursion, right? You click on recursion, we'll see it's the same page. Then we click on recursion again.
Oh, yeah.
You may think of this. Do you know this picture?
No.
So
Oh, yeah.
yeah. So in the mirror, you can see yourself seeing a mirror inside the mirror, and you can see yourself seeing the mirror. It's like recursive. It recurs all the time. This is recursion. And recursion can be used in our programs. So let's introduce an example. So there's a sequence called Fibonacci sequence. The first number is 0, the second number is 1, and from the third number, it's the sum of two numbers before it. Yeah. So you can see the pattern. 0 adds 1 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3, right? Yeah, and let's see if we want to write a program to determine a like one of the number in the sequence. Let's try. Okay, so firstly, we are going to write recursion, right? And f1 plus f, let's say f3 equals f1 plus f2, right? So the third number equals the first plus the second, then f4 equals f2 plus f3. It's a simple pattern.
Oh.
Then we can use an array to sort the sequence. So it will become f2 equals f0 plus f1, f3 equals, oh, that's not you. For recursion, we don't use an array here. So recursion, if we want to write recursion, let's write a simple function. These are some standard headers. I want to get a function called Fibonacci, which returns an integer as the result. Fibonacci. N. Here, n means the nth number in the sequence. And let's see. So the first number is 0. The second one is 1. Starting from the third, it's the sum of two previous numbers. So let's see. If n equals 1, which is the first number, we return 0 because the first is 0. If n equals 2, which means it's the second number, we return 1. Because in the sequence, the second number is 1. Okay, then if it's not 1 and not 2, right? Then we will just return, oh wait. Yeah. From, let's just leave it here. And we will return let's use Fibo, not Fibonacci, no, Fibo or Fib for the function name. So nth number equals n minus 1. Let's see, use this. N equals num n minus 1 plus num n minus 2, right? If we want to get fib nth, then we will return fib n minus 1 plus fib n minus 2, correct?
Yeah.
Yeah. Yeah, there should be no bug. So let's try to run this. So if I have whatever num in num and see out the result fib. So this is our program. Compile, run this, and let's see. We want which number do you want? You can type in or just tell me.
7.
7? Okay. 8. Let's count. 1, 2, 3, 4, 5, 6, 7. Yes. So the 7th number is 8. Or yeah. So I just output So this should work better. Yeah. So the seventh number is 8. And this is how recursion works. So in programming, recursion means a function calls itself.
Oh.
So inside this function, it calls itself. And if it calls itself, it enters the same function, then it calls itself again until n equals 1 or 2, then it terminates. Otherwise, it will keep calling the function. So you will see the computer will be like, this is a function. Oh yeah, it's a function. Wait, I mean, these are not very good examples. Yeah, so in main, we call this function. We enter the function, then it calls itself again. So we enter this function again.
Oh.
And it calls it again, and enters again. This is, so it seems cool, right? It's really cool, actually. So recursion. How do we write recursion? So for this function, it's tiny, but it's enough for us to illustrate the structure. So this part, let's call them base case. So if you get a big problem, what we will do is we will reduce the size until it is small enough, right? So for this example, we get like 7. We want the 7th number in this Fibonacci sequence. We can solve 7 because we don't know what 7's number is. We will then here it becomes the sum of 5th and 6th, but we still don't know them. The program calls fib 5. Then 5 enters here equals the sum of 3 plus 4. I mean the 3rd plus 4th number. It recurs again, and it becomes the sum of 1 plus 2. I mean the 1st plus 2nd number, which means the program keep recurs until we can solve this small problem. Yeah. So we can call this part base case, which means when the problem is small, which fits our requirement, it will return a certain value. Otherwise, it will keep calling the same function, which we just call them recursive calls. So the logic of recursion is pretty simple. Let's see. So we can write them as some did I spell this right? Pseudocode. So pseudocode is like our natural language, which is used to describe how the program works, but we don't use programming language. We use English to describe it. So if we have a function, right, it's like Fibonacci, which an integer 1, right? If meets base case, then we return something, right? Otherwise, we recursive call. Yeah. This is an example of our program. So if it meets base case, it returns or maybe terminates. Otherwise, it does some recursive call. So, and if we write them in programming language for solving certain tasks, this is an example. So if it becomes the second or the first number, we return the value. Otherwise, we'll do some recursive calls. Any question on this?
No.
No? Okay. And so we need to write base case, we need recursive calls, and we will see return is used. So when we are returning, usually we just return value, right? Usually we just write something like return 1 or return 10.
Yeah.
Or return 0. But in recursion, we will often see we return a function call.
Oh.
Here, we just treat a function. When we return a function call, what it does is when we return a function call, the program first executes the function. Or I would say calls the function and return the return value. So the program will call fib n-1 first, and after fib n-1 ends, it will return the integer, because the return type of fib is integer. Yeah. So it's hard to understand for many people because recursion involves like 10 or 20 layers. So the program will, let me draw a graph for you. Make some sense. Give me a sec, I will draw you a graph. Oh wait, never mind. I didn't find a pen. I'll just use mouse. Okay, so if we call fib like 4, right?
Yeah.
And looking at the program, we will see it returns fib3 plus fib2, right? But what the program actually does is it goes here, then the program just enters a new function called fib3.
Oh.
Then inside the fib3, it's not 1, it's not 2, so it returns fib1 plus fib2, right? But how does it work? So firstly, it enters fib1. We write n-1 first, so it should enter fib2 first. Fib2. Inside fib2, let's see, n equals 2 here. So fib2 will return, let's use RE, which stands for return, or RET. It returns 1, right? And then the program gets out of this layer. It goes to previous layer. So we are in fib3 now. We are executing this part in fib3, which is fib1. 1. And inside fib1, we return 0. And here we can see the return value of fib2 is 1. Return value of fib1 is 0. So what will fib3, what will fib3 return? If we add 1 and 0, then its result will be
1?
Yeah.
Oh.
So it returns 1. Okay. And let's see. We are currently in fib3, and we are done with the last line, which is a return. Then fib3 is terminated. The program jumps out of fib3, goes back to fib4. And we are at this part of fib4. So n is 4 now, and we are in this part. We are at this sentence. So we'll go into fib2. Sorry, forgive my drawing. It's just
It's fine.
fib2. And when we enter fib2, n equals 2 now, we'll see it returns 1.
Mm-hmm.
Return 1. Okay. And then if fib2 return 1, then fib2 is done. We jump back to fib4.
Oh, but it returns 2.
Yes.
Oh, now I get it.
Yeah, it's complex, right? It's complex. So for these type of program where we human minds are still able maybe to simulate, but you can imagine if we input the 20, how can a human think of that? Like,
Oh, yeah.
too many costs to human to simulate, right?
Mm-hmm.
So an important part in recursion is, so in recursion, a simple, I would say law or principle, a principle is belief in the program. Don't try to jump into the recursion process because it's highly complex. If we like have fib7 or fib10, it will take us like 10 minutes to draw the whole thing. Then when we write program, we have to believe, or maybe we have to acknowledge enough what we are writing. Because if we write wrong stuff, we can't just jump in and fix the bug. So it's sometimes hard to write great recursive codes. Okay, so Fibonacci is a fun thing, but we are not having a math course, so I won't go any further on that. So let's talk about some pros and cons of recursion. So good things is it's easy to understand, right? In many situations.
Yeah.
We can just focus on some few situations. If it's 1, let's return 0. If it asks for the second number, we return 1. Otherwise, we'll do recursive call. And all those jobs, like recursive calling them layer by layer, we'll leave them to the program. We don't have to do that ourselves.
Oh.
Yeah. And it can be written with shorter codes because we use only 5 lines of codes in this function to do the job, which is pretty simple. But as we all know, like free stuff comes with greater prices sometimes. So there are disadvantages. Let's not do this. Yeah. So it's not efficient because usually when we do it in other ways, we only call the function once, right? The program enters, program is in main at first, then it enters fib, then just do all the calculation inside. which is the normal case. So I will just write it. So in normal case, we don't use recursion. Means we have less. The program has less. So if we don't use recursion, the program will have only few function calls in this situation. But if we use recursion, the program will call the function many times. And these amounts increases. I think it's exponential. I think it increases at a pretty high rate. So if it's like fib 13, it will, I mean, fib 16, it will cause the program crash.
Oh.
Yeah. So for program, if it enters a new function, we will see here, the old function is still on, right? We'll go into all layers, then we terminates, go back, go here, terminates, go back, then go back. But during this time, those functions are all like, they are all turned on, or it's like, they're all running in the background, right?
Mm-hmm.
You can imagine you have an iPhone now, you turn on, like you enter one application, it guides you to another application. And when you get to like 15th application, all other 14s are still on in the background, which will cause your phone to work pretty hard, right?
Yeah.
That's similar to the program. If we just use common sense, you cut them layer by layer, all those stuff are still here. They are just not executed currently, but they are still here running. So
And we can't use recursion?
You're on the right track. I mean, not you can use recursion. I will talk about more about that. Just give me a sec.
Okay.
Yeah. So it's not efficient, as we all know, but it's more like a choice. You can pick the harder way for you, easier for a program, but you can also choose to do less work and let program do more work.
Oh.
It's more of a choice. But sometimes if you are dealing with problems, for example, if you want to get the 100, there's no way we can use recursion for that. I don't recommend recursion because it will cause the program to crash, definitely crash. So it's more like a choice, as I said about data structure last time, right? So it's more of a choice. You have to balance the pros and cons. So if you are sure that the problem size is small enough that you can use recursion and it won't crash, then recursion can save your time, save your life. But if you're unsure, then writing recursion still take minutes, like take 5 minutes or 10 minutes for a complex problem. Then if it doesn't work, you have to erase them and rewrite, which is much harder for you. So it really depends. But it's important to keep in mind, recursion will get much, like it will cost much more memory and have much more pressure on program once the problem size gets big. Oh, oh, Mr. Kingston, are you on? Oh, never mind. I thought he's on. I thought he's talking to us. Okay. Yeah, here's what I try to say. So it may cause runtime error, which means the program runtime error. Let's open the tab. Runtime error, which is a result we will get for some judging system. Program error occurs when the program is running. That's all we need. Yeah. A program error that occurs while the program is running. And sometimes using recursion to a problem with huge sites will cause runtime error. So it's important to keep in mind, but for many situations, we can still use recursion, and it's really powerful.
Oh,
Okay. Let's see, how many time do we get? 31. We still have 15 minutes, so this is all about recursion. Any question on them?
no.
No? Okay. I would say we get a genius in the club, honestly. It took me, I don't know, half a month to get all of this. Okay. After understanding recursion, we can start writing really powerful codes. So let's see, flood fill. Let's introduce a classic type of question, which can be solved using recursion. So flood fill, question like this. Okay, I don't see any good examples here. Said, I'll just make our own example. Okay, so if we have a matrix, okay, if we have a matrix,
Mm-hmm.
okay, if we have a matrix and it's the form of 0, 0, 0, 1, 1, 1, 0, 1, 1, 1. So with places, with like for each position, if it's 0, it's a wall. If it's 1, it's a spot where you can step on. So if we start, let's see. I mean, this example is a bit dumb, but whatever. Okay, so if we start from here and we want to write a program that brings us to this spot. So we start from 1, 0. What happened? Oh. 1, 0. We'll go to so we start from the spot 1, 0. Index starts from 0. So and we want to go to 1, 2. It's like going, yeah, this is like going in a roadmap or something, and we can already write a program to solve this. So any idea?
Could just try it out first.
What?
No, and just
No?
go. Yeah.
Okay. Yeah, because we just cover recursion. Put you in the spot. I shouldn't do that. Okay. So let's start with pseudocode. So when we are thinking about general approach, right? can use pseudocode to understand what we should do. Now we start writing the real code. Right. So let's have a function called path finding. We have a x and a y. Oh, I mean use row and column, which is our current row and column. Right. So if this is if this equals 0, or if we are on the wall now, there's something wrong. We should return. Right. And if this equals 1, I mean, this is redundant because we've already returned if we are 0, then the only possibility left is 1. So here we are at 1 now. So we can move. So we can move with a certain order, right? Here I will use an array to store use two array to store our moving direction. So if we are moving left, then if we are moving right, we'll increase 1 on x, but our y will remain the same. If we are going left, our x or row will decrease by 1, y will remain the same. If we are going up, we will decrease y by 1 because the index goes from 0 to 1 to 2. Okay, then we will increase 1 if we goes down. Okay. So we write a for loop. Oh, I shouldn't just write the code. I said it's pseudocode. Okay, let's use pseudocode still. If at wall return. Otherwise we are at available spots. An available spot. Then we can for all directions. We move path finding. Yeah. We still need something to, let's see, what do I miss? Any thoughts?
So if you put in a number, it just goes to all directions.
Oh yeah. Yeah. I'm right. So if our destination is not out of bound, because it can get out of the matrix, and it is not a wall, because we can't go on a wall. Then we move. So to simulate move, we can use row plus dx, column plus dy in some way. Then we will call the function at new position. I think that's it. And when we get to our ideal destination, which is 1, 2, we can use a global variable. We can use a Boolean, global Boolean, font, or maybe, yeah, font equals false if at ideal position font equals true. Yeah, I think this is all we need.
Oh. And what comes out
What?
when we do that? When we process that, what comes out?
Can you say again?
If we process this code, what comes out of it? Like what's the answer?
Answer? Oh, for our current code, I haven't wrote, like we haven't write anything to record our path and things like that. So all we can get is yes or no. Can we go to our destination? Yes or no.
Okay.
So if we get to there, then the font will be true at some position. Otherwise, it will be false. Yeah. Let's, do we have, yeah, we still have a few times. Let's just implement it by the end of the meeting. Yeah, I'll just copy these parts. Equals false. Go for global variable, Boolean variable, Boolean, so global variables are false by default. So we don't have to set them false, they are just false.
Okay.
I will use void because we don't want to return anything here. We just want to make a path finding. Obviously, path finding is too long a name, so I'll use DFS, which stands for Depth-First-Search. I mean, this name is fancy, but in common sense, it's just we choose a row, go straight to the end until we know it doesn't work. We exit, we choose another row, go straight to the end. That's basically what we are doing here. Okay. So have a row, column. If actually we can remove this because before we make any moves, we'll detect if our destination is a wall. So we don't, it shouldn't be possible that we are currently on a wall. So we will just go to this part. If row equals, what's our destination? 1, 2. Row equals 1. And, oh, did I cover this? I think I did, right?
Yeah, you covered it.
Okay. Equals 2, which means, yeah, so your position 1 equals true, will return. Otherwise, for here, we use 2 arrays to store the moving directions. It will be easier for us to actually move them. So, and mx, which is, I mean, I use this. Moving on x, moving on y, we'll just mx and my. dx equals row plus mxi. So destination x equals current x plus moving distance.
Oh.
Yeah. I can use dy, which is the same. Okay. So our new position would be dx dy. So here we need to detect if our new position is out of bound. So we need 2 variables outside, int n and m. So n is row numbers. So there are n rows and columns. Okay. If our new dx is greater or equal to 0, because our index starts at 0, and dx is smaller than n, because since our index starts from 0, it should be 0 to n minus 1. Yeah. And same as dy, it should be greater or equal to 0 and smaller than m. Oh, but this is only one part. So these parts make sure we are not out of bound. And I haven't used, let's use a grid. Use this to, matrix. Matrix equals, I will initialize that part later. Okay. And matrix x dy is outside. Okay. Not equal to 0, which means our new position shouldn't be on a wall. We will make a call now. So DFS. We'll make a call on new position. And this is enough. This is our path finding program. It's pretty smart. It can do all the job now. So should I enter something? Yeah. Okay, I almost forgot that we actually need a matrix. Okay. I will give it some more spots because to prevent the. So usually when creating arrays, we will give a bit more spaces. Prevent some. So if we are asking, like if I gets out of the bound, it will cause the program to crash. But sometimes if we make it a little bit larger, it will prevent these problems. Like sometimes the program just crashed even though you didn't do anything illegal, simply because array is still not reliable. So we will give a bit more space to prevent possible runtime error. Usually we just give 5 or 10 more positions. So if n equals 100, we will, so if required number, we'll initialize to 105. Or maybe, so I'll just use 1010 here. And we'll read in the array. Did I? Yeah. CMA. Okay. Then we will do a DFS. And our starting position is 1, 0. So we start from row 1, column 0. And if we font it, then this font will become true. Yeah. So if font, but congrats. In the right path. Oh, that's it. Let's try to run. Oh, actually, we still have to input the matrix by hand. So it's
Oh.
still fun parts. Oh, what happened? Wait. Do we not get there?
Hmm?
Wait, we didn't get there. What happens? It's weird. Let me think of it. What happened here? Oh, we haven't initialized n and m. So yeah, it's embarrassing. It's an embarrassing problem. We should think. So here, n and m, since they are global variables,
Mhm.
they equal 0 by default, right? They are 0 by default. So I didn't initialize them, which will cause them to become 0. Then here, there's no way they can pass these conditions because n is 0. You can't be greater or equal to 0 and smaller than 0 at the same time. So this will cause an error. Let's read in and m, and they should be 3. So I will input 3, 3, matrix. Seriously, what happens here? That's the worst moment ever. Okay, let's see where the bug is. Matrix ij 0, 1, 2, 0, 1, 2. mxi, myi. I mean, that's pretty sad. If we can find the right path,
Mhm.
what happens? I'm somewhat confused. Okay, and this is normal though. This is normal for competitive programming because just get stuck sometimes. So mx, my. We will go this way, so it should be 0, 1, 0, 1. Goes down, goes right. Okay, dfs, dx, dy, row plus mx, column plus my. What happens here? It's not 0. So it costs 1, 0. Yes. Input n and m, then we input the matrix. Nothing seems wrong. What we should do now, it's another technique. It's called debugging codes. So we will output the current position debug. So for this part, it simulates how the program goes to different positions. This should work here. Oh, did it just copy the wrong stuff? 3, 3, matrix. Okay, so here we will see a bug. That's the part I forgot to tell you. So 1, 0, 1. So we can see 1, 0 should be a 0, 2, 0, 1, 0, 2, 0. Yes, that's the most important thing. So we use a Boolean error. I mean, Boolean don't use an error. Boolean array, which we can use Boolean visited. They are all false by default. And when we visit a certain position, so we will set visited row which tells them we visited this position. And here, when we are looking for new positions, it has to be not visited. So visited dx dy, we need a not here. So this tells the program if we haven't visited some place, we will go there in the next round. So this is necessary. Otherwise, we'll fall into infinite what's that? Infinity recursion. Visited. Okay, here's the naming problem. It should be visited, but I wrote it as visited. So it's really a vivid example of debugging. This happens a lot, especially when you're solving harder problems. You can get stuck and spend half an hour debugging. You realize you wrote something. Okay. Here we can run the program. 3, 3. We will input the matrix. Then for these 4 lines, they are the searching order. So we start from 1, 0. Then we are at 2, 0, which is here. Oh, yeah. Then we goes to 2, 1, which is here. And then 2, 2 here. It doesn't output 1, 2. The main reason is, let's check the code. If it's 1, 2, it returns before it prints anything. So it doesn't print 1, 2. But we know that it's right because it tells us, congrats, you succeeded in finding the right path. Okay, so that's a cool one, right? After learning recursion, the searching can be.
Could you put the codes, copy it, and paste it in the chat so I can just copy and paste it on my.
I can actually send them in the classroom.
Okay.
Would it be easier? Yeah.
Yes.
Okay. They're cool, right? Pretty cool.
Yeah. But it's hard.
Yeah, but after learning recursion, you can already write a program to teach your friends how to get out of, go on a roadmap. Right, that's pretty fun. Okay, so recur, let me see, recur. Yes. And many important pathfinding programs are relative to this one. So DFS, it has a fancy name, but that's all it does. Yeah, I should don't forget to, yeah, never mind. I will just leave the print statement there so we can visualize how it works. Yeah. Okay. I will also include this one. I think that's actually all for today. I will, before you go, I'll just upload them. You can get them. Where is it? Wait, where is it? Okay, they're here. Okay, recursion, DFS. So depth-first search, which is DFS for short, it's useful for us to finding a path. And you will use it really often if you are writing some questions relative to graphs and path finding stuff. Okay. Okay. What's the date? May 12th. Yes. So, program. So the first one is the recursion. The second one and the third one are just some lectures. They are in Markdown though, but you can read them in the text. It should be the
Okay.
same. Yeah. And that's all.
Okay, thank you. Bye.
See you.
How'd it go, Kevin?
Great.
Sounded pretty good. You
Yeah, and we just went through that first search and wrote I just like went through a simple pathfinding program.
Was
That's
it
pretty
just,
fast, I would say.
was it just Kara today?
Yeah, just Kara.
And she understood recursion?
Yeah, I'm surprised.
Oh, she's smarter than I am, that's for sure. That's good.
Smarter than me.
No, I don't
we
think
draw a graph of how recursion exits,
Yeah.
which is great.
Yeah, I saw you go through the Fibonacci series. I thought, yeah, it's good idea. I used to use that with Python. But anyway, great job.
Yeah.
All
I
right,
still
Kevin,
hope they can come though.
what's
We
that?
get only Kara for these meetings.
I know, it's too bad. Yeah, I'm not sure what to suggest. I've had a number of kids tell me that they're not returning or wasn't early. But I mean, we'll keep going for a couple more weeks, and after May long weekend, probably it's time to call it quits. And unless Kara's really interested, we'll keep going. What do you think?
I think Kara is talented,
Yeah.
I would say.
Well, this is a good opportunity for her then, if you don't mind. It's great.
Yeah.
All right, Kevin, I should get going, but take care and thank you again. Thanks for all your hard work on this.